Okay, so today we're talking about section 5.3, and in that we'll be talking about polynomials, the graphs of polynomial functions and how they behave, and we'll be focusing on polynomial functions that are greater than a second degree. So let's look and see what would happen with these. Okay, so our basic y is equal to x squared is a polynomial. Okay? It's heading up towards infinity as x is positive, and then also for the negative values of x, the graph is also positive because you can square anything and keep it positive. Okay? Now if we look at x to the fourth, okay, that's the blue line, and we see that the same phenomenon is happening, that as x is positive, the function values are staying positive, and as x is negative, the function values are also staying positive. That's because if you take something to the fourth power, it will always stay positive as well. So these graphs are very similar in shape. You can see that they're both taking off to infinity, but that x to the fourth is going to infinity much more quickly than x to the x squared. Okay? So we could also look at x to the sixth, and you'll see again the same phenomenon happening. Sixth is an even degree, and that will force all the negative values to go positive. It will be going to infinity, but much more quickly. And we'll see that happening with even any even degree, say to the 22nd power. Okay. That's the purple line. And again, the negative values are staying positive. Okay. What you might see, though, I don't know if we'll see it happening here. Yeah, let me come in. Okay. The closer, for values in between 0 and 1, or 0 and negative 1, those fraction values, the graphs are actually, the red, remember, is the x squared, is much more curved, and with each iteration, the graph is flattening out more. Okay, but basically the same shape. Okay. All right. Now let's look at our basic x cubed function. Okay. Now with that, as x is positive, cubing anything will keep it positive and it'll take off to infinity. And with negative values, a negative value cubed still stays negative. Okay, so this is our basic shape of x cubed. We also have, let's try another odd value, x to the fifth. Okay. So here's our x to the fifth. It's a little more flat in between these values of 0 to positive and negative 1, but that it takes off to infinity and negative infinity, okay, because taking anything to the fifth power will still keep negative values negative, okay, or positive values positive. So it's still taking off to infinity, but it's getting there much more quickly. Okay. We could also look at x to the seventh. Okay. So again, more flat in between here, but it will take off to a positive infinity and negative infinity more quickly. Okay. So let's look at like x to the 27th, any other odd value, and see if it follows the same path. And again, there it's flattening out much more in between negative 1 and 1, but that it's taking off to negative infinity, this furthest one in, and positive infinity much more quickly. Okay. So really, the graphs of functions are determined by the power of the exponent. Okay. So let's start from there. Now notice I was just showing you a polynomial with a single term. So this is known as the power function. Okay? So with the power function, it's of the form f of x, because it's a function, and it can have a constant in front of it, we won't care, k times x to some power. Okay? And then to summarize what we were saying, there's 4 different possibilities that we have. Now, the first we saw looked like this. Now, this will happen if k is greater than 0. That is, if we have this positive constant here. Okay. So if we have a positive constant, okay, and it's an even power, then we get a concave up. Now, if the constant is less than 0, that is, if it's negative and it's even, then we'll get the concave down. On the other hand, our power could be odd, and if the constant is positive, it'll have this sort of a shape. And if the constant is negative, it will flip like so. So let's see what we can say about what happens as x approaches positive infinity. Okay. Well, if x is approaching positive infinity and the constant is positive, then the function is also headed to positive infinity. And since it's even, as x goes to negative infinity, well, the function has to stay positive as well, and we'll take off to positive infinity. Okay. So what we're looking at here is we're now looking at the end behavior. Okay. Now, if the constant's less than 0, we get the concave down. So as x goes to positive infinity, this direction, the function's taking off not to positive infinity, but to negative infinity. And the same was happening as x goes to negative infinity. Now, if it's odd, things happen differently. Okay. As x goes to positive infinity, the function takes off to positive infinity as well. But if you're looking at what happens when x goes to negative infinity, okay, the function is taking off then to negative infinity. Here, as x goes to positive infinity, so now we're looking out this way, what's happening to the function as we move this way is the function is diving towards negative infinity. But if we look at what happens as x gets very, very negative, the function then starts taking off and becomes positive. So as x goes to negative infinity, the function now is going to positive infinity. So this is just where we have a constant times x to some power, even or odd. And now let's look at some different functions, okay? So we're going to vary variations of the power function. Okay, so what we're going to do now is we're going to vary the power function, okay, and see what happens. So by varying the power function, what I'm doing is adding in some extra terms. Okay, notice that the power function is written, this is now a polynomial, and it's written in descending order. Okay, we don't have an x squared term, and that's fine. But notice that the leading term is 5x to the fifth, or 5x to the fourth. Okay? Now, x to the fourth is an even function, is an even power. Okay? And so we can see when we look at the graph that it basically is acting at large values of x, okay, towards the end here or towards the negative. It's still taking off to positive infinity. Now in here we have a little bit of a variation of what happens, but the end behavior is still the same. Okay. Now let's look and see what we have when we have negative x to the sixth. Again, written in descending order, so we varied the leading term. Okay, the leading term is a negative coefficient, and x to the sixth power, which is even. So the leading coefficient is, or the leading term is negative 2x to the 6th. Okay. And when you look at its graph, it has the same ending behavior of negative x to the 6th. So negative x to the 6th would look like this. As x gets very large, the function is still diving, or as x gets very negative, the function still dives. Now in between, we have a little bit of variation. It's not just the nice concave down. Here's another. Here's a polynomial, 3x to the 5th, and then we've added a couple other terms to it. Okay. Now the leading term is 3x to the 5th. Okay, so it is a positive coefficient with an odd degree. And when you look at its graph, it is very similar to the graph of x to the 5th. X to the 5th would look just like so. Okay. In between, we have a little bit of variation, but at the very large values of x, positive, the function is going positive, and at very large values, negative of x, the function is taking off to negative infinity. Here we have negative x cubed. Again, we varied it slightly by adding extra terms, but the dominant term, the leading term, is negative 6, so there's a negative coefficient, and an x to a 3rd power. And when you look at its graph, again, the end behavior is very close to negative x cubed. Now there's quite a bit of variation here, but the ends are very similar. Okay? They have the same end behavior. So, let me give you some, now that's the variations, and let me give you the definition of what a polynomial is. Okay? So definition, a polynomial can be written as. So we'll have f of x is equal to a sub n x to the n plus a sub n minus 1. Okay, so these little subscripts, I just read a sub whatever, and then x to the n minus 1 power. And we can keep going for as many terms as we need till we get down to a sub 2 x to the 2nd power, a sub 1, x to the 1st power, and a sub 0, which we usually write as a sub 0, but remember we could write that as times x sub 0, or x to the 0 power, because x to the 0 power equals 1. Okay, so this is going to be your constant term, okay, because there's no variable associated. X to the 0 is 1. Okay. Now, this is going to be the leading term. Why is it the leading term? Well, because if we look at what we're saying with the exponents, if this is the nth power, then this one is 1 less than your nth power. Then the next one would be 2 less than your nth power. Okay, so we'd be writing it in descending order. So example, if n is 5, this would be x to the 5th, this would be x to the 4th. And these a sub n's, a sub n minus 1, a sub 2, a sub 1, these are the coefficients. So I'm just going to label that as the a sub I because there's various different subscripts here, are the coefficients. And that'll help us. We can make a summary then for any polynomial. We can again write our 4 different possibilities. It can be that the nth power is even. It could be that the nth power is odd. Okay. And then we're going to be concerned about a sub n here, this coefficient. Is a sub n positive? Well, if it is, then the shape of the graph will have an end function like this. Okay. I don't know what's happening in between here. Okay. It could be looping up and down. It could be doing a lot of things. Okay. Now, if the coefficient is negative, I don't know what will be happening in between, but at very large values, the end behavior has to be pointing downward. Now, if the coefficient, the leading coefficient is positive and the degree is odd, then the end behavior actually looks like this. I don't know what will be happening inside of here, but I do know this. And if the leading coefficient is negative, then the end behavior must be happening this way. Okay. Now let's talk about what's going to happen inside of here. Okay. There could be lots of things happening. So there is a relationship and that relationship, there's a relationship between the degree of the polynomial and what we call the turning points. Alright, so let's say we have this function. Okay. Our graph looks like so. Something like this. Now, I don't even know what this function is. We'll just call it f of x. Okay. I know a few things about this function, though. I know f of x has a leading term that is even power, because they're both taking off to infinity. And I also know that a sub n, the leading coefficient, is positive. Even if I don't know what this graph is, I know the leading term is a leading power with a positive coefficient because of the end behavior. Okay. Now let's analyze what's happening. Okay. Here we have a local minimum, and here we have a local maximum, and here we have a local minimum. Okay. So let's just call this x1, x2, and x3. Okay. They will occur at these points. Okay. Now, for values from negative infinity up to x1, this function is decreasing. Okay. So we decrease here. Also, in between x values of x2 and x3, this function is also decreasing. Now, between x1 and x2, the function starts increasing. And from values of x3 through infinity, the function is also increasing. So remember, when we're talking about the local min, we're talking about the y value that occurs at x1. If you want to talk about this point, or this point, in this case it's a local maximum that occurs at x2, here's a local minimum that occurs at x3. Okay. If you want to talk about these points, these are called turning points. Now, let's say that I know what the value of this, or the equation of this function is. Let's say it's f of x is equal to x to the fourth minus x cubed minus 4x squared plus 4x, let's just say. Now, what I can tell from here, again, is that we were correct. It's an even power with a positive coefficient. Remember, the coefficient here is 1, positive 1. Okay, so this is a 4th degree. And then I could ask myself, well, how many turning points does the 4th degree have? And we see that it has 1, 2, 3 turning points. Now, it doesn't always have to occur that there are 3 turning points. But one thing that we should make note of is this, then. It could have fewer. It could have 2 turning points, 1 turning point. It doesn't matter. But the important thing is that it can't have more than 3. So we'll note that a polynomial of degree n, so you get to pick the degree, will have at most n minus 1 turning points. Doesn't have to have all of them, but at most it will have. So, for example, if we had x to the 10th plus blah, 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 however we vary it, it can have at most 9 turning points. So we'll see this happen. Now let's talk about the zeros of the function and their multiplicity. So this is also known as the roots, or the solutions to where the function equals 0. That's why they're called zeros. Some people call them that. Okay, so let's look at this graph. So say it's something like this, and let's say this is the point negative 3, 0, and this is the point negative 1, 0, and this is the point 2, 0. So the solutions to where this function f of x equals 0, well, it occurs where the function equals 0 and at the x-intercept. So if we were to solve f of x equals 0, we would get x is equal to negative 3, negative 1, and positive 2. Now, I can't really say anything about the degree of the polynomial too much. I mean, I can say, well, it's got to be an even degree, and because it's pointing upward, and it must be a positive coefficient with it. But if it's an even degree, I also know that there's needs to be an even amount of solutions. Like if this was a 4th degree, I would expect that there would be 4 solutions. If it's a 6th degree, I would expect that there would be 6 solutions. So this is a conundrum. So what does that mean? Well, I'd like to point out that there is some different behavior that the graph does around these solutions. So at x equals negative 3, the graph starts on one side and passes through. It also does the same thing. It passes through that x-axis here. However, on this one, it bounces off the x-axis. And this will have to do with what's called the multiplicity of the zeros. Now let me tell you this. if we look at this, let's say that the function is written in factored form, not expanded, x plus 3, x minus 2 squared, and x plus 1 cubed. Is it reasonable to think that this function represents this graph? Okay. Well, the first thing we would want to check for, remember that this is a positive even degree because of the end behavior. Okay. So let's see if this is an even degree. Well, if I was to expand this x cubed, x plus 1 cubed, I get x cubed plus blah, 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 blah. Let's see. As an aside, let me show you what I mean by my blah, 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 blah. X plus 1 cubed would be x plus 1 times x plus 1 times x plus 1. Okay. Now, let's remember how we multiply these binomials. Let's first work with this, and we'll just bring down the x plus 1. Okay. Now this, by FOILing, we know becomes x times x is x squared, then plus an x plus another x, which is plus 2 x's, and then plus 1. So when I multiply these together, the x and the x were the dominant term and became x squared. Now, when you're multiplying the binomial and the trinomial, remember you have to distribute the first one through, so that would become x cubed plus 2x squared plus x. But we'd also still have to determine and distribute this 1 through, so we'd be adding x squared plus 2x's plus 1. So once I combine like terms, I get x cubed. Here's an x squared and an x squared plus 3x squared plus an x plus 2x plus 3x, and then plus 1. So that's what happens if we expand this portion of it. When we just expanded this portion, notice that the x and the x became, the x and the x squared became x cubed. And so the dominant of this one times the dominant of that one became our new dominant term. Now, if I was to expand this one, remember that's x minus 2 times x minus 2, and if we were to FOIL that, that would be x squared minus 4x plus 4. Now what our function says is that I need to multiply these two things, which is going to be a lot of work because I would have to distribute the x squared to every single term, the negative x to the fourth to every single term, the 4 to every single term, collect like terms. Okay. But when I do that, remember, let's just see, we're trying to check is this positive and even? Okay. Well, the dominant term here would be x squared times x cubed, which remember when you're multiplying with like bases, you'll add the exponents. So the dominant term of whatever I multiply this out to be is going to be an x to the 5th. Plus a whole bunch of other math, right? But I'm still not done. I would have to multiply that by x plus 3. Okay? And so I would have to take the x times everything in this plus the blah, 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 blah. Okay? But in the end, it wouldn't matter. The leading term would be x times x to the 5th. So this is a 6th degree polynomial. We get x to the 1st times x to the 5th for the dominant to get x to the 6th. And it does have a positive coefficient, which is just 1. I hope this makes sense. All right? We don't want to go squaring all of these things out and squaring them and cubing them and multiplying them together. So we just need to look. From here, it's reasonable. If I was to cube this, I would get an x cubed. So there's a 3rd degree. This would become an x squared. So I get 2 more degrees for an x to the 5th. Plus this is to the 1st power. So an x to the 5th plus 1 is x to the 6th. Okay. So that's reasonable. Now let's double check the zeros of the function. Like if we were to solve this being equal to 0, well, we can just read what would make, since it's all multiplied together, we know that anytime any of these factors go to 0, then the whole function would be equal to 0. Okay? So the one that's going to do that here is x equals negative 3. The one that does it here is positive 2. And the one that does it here is negative 1. Okay? So if x is any of these values, this entire function goes to 0. Negative 3 plus 3 would be 0. 0 times anything is 0. 2 minus 2 is 0. 0 times anything is 0. Negative 1 plus 1 is 0. And again, anything times 0 is 0. So when it's written in factored form, we can see the zeros very clearly. And now with these zeros, it makes sense also from the zeros that this graph represents this. Okay? So if negative 3 is a 0, then negative 3, 0 is an x-intercept to the graph. If negative 1 is a 0, then negative 1, 0 is an x-intercept to the graph. And similarly here with 2. So the reason why we talked about all of this was to determine, okay, now we've determined this is a 6th degree polynomial, and we only have 3 values of x that will make the function equal 0. Okay? That is, we have 3 solutions to where the function equals 0. So I just talked you through about reading these. Let's actually use the zero product property and see what happens. Okay. So if we had f of x is equal to x plus 3 times x minus 2 squared times x plus 1 cubed. Okay. Now if we want to solve where the function is equal to 0, well, we just have to set it equal to 0. Okay, let's look at the factors then. Okay, we have 3 things being multiplied together, so it's either then that x plus 3 equals 0, x minus 2 squared equals 0, or x plus 1 cubed equals 0. So from here, it's directly obvious that x is equal to negative 3. Now I'm going to expand this one just so we can see this happening. This means x minus 2 times x minus 2 equals 0. And again, if we use the zero product property, we have either that x minus 2 equals 0 or x minus 2 equals 0. Now these are linear, very easy to solve. We'll see x equals 2 or x equals 2. So truly, that value of x where x equals 2 occurs twice in the function. Similarly here, this means x plus 1 times x plus 1 times x plus 1 equals 0, which we can split into 3 different, using the zero product property. It's 3 different linear equations, and from each of them, we get the solution with that x is equal to negative 1. So now let's count the x's when we've done it longhand. Here's 1, 2, and 3, 4, 5, and 6. So there is actually 6 solutions to this 6th degree polynomial. It just turns out that they have different what we call multiplicities. X equals negative 1 has a multiplicity that it occurs of 3. Because it occurs 3 times. X equals 2 has a multiplicity of 2 because it occurs twice. And x equals negative 3 has a multiplicity of 1 because it occurs once. Now, since these are linear inside of here, we could just read it from the powers. If it's not linear inside of here, we're going to have to do something else. So x equals negative 3 has a multiplicity of 1, because this is linear. There's no x squared here or anything. X equals 2 has a multiplicity of 2. X equals negative 1 has a multiplicity of 3. Okay, let's look at a different graph and see what we can determine from it. So let's say we have a graph that bumps, and then crosses, and comes down, and then crosses. Okay. And let's say this is the point negative 3, 0, and that this is the point negative 1, 0, and that this is the point 4, 0. Now, I can't say exactly what degree this function is, but I can say, I can classify it. F of x is a positive even degree. I can say that because I just look at the end behavior. I don't worry about what's happening in here. Just by the end behavior, it's taking off to infinity in both directions, so I know that there's a positive even degree to this. I can say a few things about the zeros. Okay. I know that negative 3 is a 0, that negative 1 is a 0, and that 4 is a 0. That is, that they will solve, if I was to solve f of x equals 0, these are the values of x I would get. Now let's say anything about the multiplicity. Well, at negative 3, let's talk about its behavior. At negative 3, this function bounces. Okay? And if it's to do that, okay, another word for bounces is that it's tangent to the graph. Oh. And then, well, we'll continue with this and then we'll go back. At negative 1, it's going to cross, and at 4, it crosses as well. Okay? That is, it passes through the x-axis. Well, I don't know what that means about multiplicity, so let's go back and examine what we had here. Okay. Now, here we said at x equals negative 3, we had a multiplicity of 1. At x equals negative 1, we had a multiplicity of 3. And at x equals 2, we had a multiplicity of 2. Okay. Now, when this happens, x equals negative 3 with a multiplicity of 1, it crossed. At negative 1 with a multiplicity of 3, it also crossed. And at x equals 2 with a multiplicity of 2, it was tangent, that is, it bounced. Tangent or bouncing. So 1, 3, and 2. Now in this one, we have behavior about being tangent and crossing. But there's no way I'm going to actually be able to tell you what the multiplicities of these zeros are, because I don't know what degree we're talking about here. Are we talking about an 8th degree, a 10th degree, a 12th degree? I don't know. Now on this one, when we looked at the multiplicities, if you add up the multiplicities, 1 plus 3 is 4, plus 2 is 6. And remember, we were in a 6th degree. So whatever these multiplicities are, they will have to add up to the even degree. Okay, if we were to add them. But I can't really say what the multiplicities are unless I have the equation directly. Okay. But I'm thinking that there's a pattern here. Perhaps. Now here I had a crossing and the multiplicity was 1, and here was a crossing and the multiplicity was 3. these are odd numbers. And it will turn out that this is true, that I can't say what the number is, but I know this multiplicity has to be odd, and this multiplicity also has to be odd, because of the behavior that they exhibit by crossing. Here, we had a multiplicity of 2, which is even, so we said the graph was tangent, and that is true. Anytime the graph is tangent, it will have to be an even degree. So this is all I can really say. If I was given this graph, I can say that the function f of x here is positive even degree. I can identify the zeros of the function because I can see the x-intercepts. I can identify the behavior of those, and so I can tell you whether it's an even or odd multiplicity. Let's try another. Now with ours, once we get functions, we'll actually be able to do some more work with them. But here's another example. Let's see if we can just do some identifying without the function. Let's say the graph does this. And let's say this is the point -5, 0. Why not? -1, 0. And let's say this is 3, 0. Okay. What is it that we can say about f of x? Okay. Well, to be able to say anything about f of x, I look at the end behavior, and I have a negative here and positive here. So I know that the leading coefficient is positive, and that this is an odd degree. I do not know exactly what the degree is, but I know from the end behavior that it is a positive odd degree. Okay. Now let's look and see what we can say about the zeros. Okay. We know that x equals -5 is a zero, or a solution, or a root. So is -1, a solution, a 0, or a root. These are all saying the same thing. Now, if I want to talk about the multiplicity of these zeros, to do that, I have to examine the behavior. So at -5, the graph actually crosses the x-axis. At -1, it is tangent. And at 3, it's also tangent. I get that just from reading the graph. And so what that will mean then is that if it's going to cross, it has to have an odd multiplicity. If it's going to be tangent, we can say that it has an even multiplicity. So that's all we can really say, but if we were to add these up and we knew what the odd degree is, it would need to be an odd number, okay? Because the multiplicities will need to add up to the degree of the polynomial. Now this behavior about crossing, that is, it goes from the x-axis, leads us to a very important theorem, okay? It's called the intermediate value theorem. So theorems, I just abbreviate THM. Theorems are something that's true, and we don't have to prove them, we can just use the results. Okay, so we let f be a polynomial function. So remember, not all functions are polynomials, so if it's the case that f is a polynomial function, the intermediate value theorem, okay, so this is the important part, the intermediate value theorem, says that if the function evaluated at some a value and the function evaluated at some b value have opposite signs. Okay, so like if one's positive and the other's negative. Okay, that's what they mean by opposite sides. If that's the signs, then we can say there exists at least one, could be more, one value C that's between A and B. Okay. That is where the function was evaluated at one sign and where the function was evaluated at the opposite sign. Where if you take the function and evaluate it at C, it has to equal 0. Okay, so let's try and think about what that means. We want f of A and f of B to have opposite signs. Okay, so in this case, we have one example of this. Let's say this is A, then down here is the point A, and then the function evaluated at A. Okay, that's an ordered pair. So f of A is over here. Okay, you go over to A and down to f of A. Okay. This has to be negative as we've drawn it on the graph. Okay. Now let's say here is B. Then this point is the function evaluated at B. So this looks like this. And B is positive. So we have what the criteria for the theorem says. We have a polynomial function. We have some point A that is a negative sign and some point B that has a positive sign. It could also be the reverse, but they have opposite signs of each other. Then the theorem says there exists a point C such that the function equals 0. And it's true. Okay? Here is where our function is equal to 0. And specifically the C value that does it is negative 5. So this will help you when you're looking for the zeros of a function. If you find 2 points where one's positive and where one's negative, you can stop and start looking in between those two values for where the function equals 0. Okay. What's an example of this? Let's do an example of this. Okay. So, for example, it's very helpful. When you have the graph, you can clearly see it happens. But let's say f of x is equal to x cubed minus 5x squared plus 3x plus 6. And we need to show there are zeros between x equals 1 and x equals 4. Okay. There are zeros. Alright, well how are we going to do this? I would start this way. Evaluate your endpoints. F of 1 is 1 cubed minus 5 times 1 squared plus 3 times 1 plus 6. So this is 1 minus 5 plus 3 plus 6. Let's see, 10 minus 5 is 5. Okay, so this is positive. Let's look at f of 4 and leave some space here. 4 cubed minus 5 times 4 squared plus 3 times 4 plus 6. So 4 cubed, 4 times 4 is 16, times another 4 is 64. So 64 minus 16 times 5 is 80. 6 and 5, 3, 6. So minus 80 plus 12 plus 6. 12 and 6. Okay, let's see how we can do this. So 80 minus 64 is 6. So negative 16. Plus, did I do that right? Yes, plus 12 plus 6. Okay, so negative 16 plus 4 is minus 4 plus 6. So this thing is a negative 2, and this is negative. Okay. So these are the two bounds they've given us. So when I take 1 and I evaluate it in the function's positive, and when I take 4 and evaluate it in the function, it's negative. So now I know that there's a 0 in between here. At least 1. There could be more. Okay. Now if I'm doing it by hand, let's just evaluate the next one. So 2 cubed, the next integer. Okay. It doesn't mean that those zeros were going to actually occur at integer values. Okay. So 2 cubed is 8, minus 2 squared is 4, times 5 is minus 20, plus 6 plus 6. So 12 and 8 is 20. 20 minus 20 is 0. Okay? So we've shown that there's at least 1. Okay? X equals 2 is a 0, because the function equals 0. Okay? But let's evaluate f of 3. So 3 cubed minus 5 times 3 squared plus 3 times 3 plus 6. 3 cubed is 27. 3 squared is 9 times 5 is minus 45 plus 9 plus 6. And what we'll see then when we add all of this up is that this will be negative 3. Okay. Did I do this right? This is positive 2. Sorry, you guys. This is positive 2. Okay. So, at f of 1 it's positive, and f of 4 it's positive as well. And if we're supposed to show zeros, our intermediate value theorem doesn't say anything about the same signs. But we were told to show it. So then we can evaluate 2, and we find there is a 0. We just got lucky with that. And then we evaluate 3, and find out it's negative 3. So what that means, if we now shorten the intermediate value theorem, let this be our first one. Here's a positive value, here's a negative value. So in between 1 and 3, there must be a 0, and we found it at 2. Now in between 3 and 4, we have a negative value and then a positive value. So again, by the intermediate value theorem, there must be a value here that will solve this equation to make it equal to 0. Now we're not going to do that at the moment, but I will show you the graph then of what it looks like. And it turns out, so here's our f of 1, which is 5, and our f of 4, which is 2. The intermediate value theorem didn't say anything about that. But once I looked at f of 1 and f of 3, they changed signs, so there was a 0. And now I know there's a 0 between f of 3 and f of 4, because f of 3 is negative and this one's positive. And you can see there is a 0 there, and it's more than likely irrational. Okay. But we know it exists. Yes, so this was an x cubed situation. Also notice that we have 2 turning points here. So that's the third degree, and we have 2 turning points. Alright, now let's put all this together and actually do some of the most fun connect the dots that I think there is. Okay. what we need to do then is, let's say f of x is equal to negative 2 times x minus 1 squared times x plus 3 times x minus 5 cubed. And we're going to sketch this graph. So to sketch in a graph, we always need our important points. Okay? One is the y-intercept. Okay? So if you do that, you're going to find f and evaluate it at 0. Okay. Now this is in factored form. Don't go expanding this thing out. Okay? I do not want to cube this and then square that and multiply those and then multiply by this and then finally multiply by a negative 2. We don't need to do that. We can find f of 0 by just substituting 0 in the factored form. So that's just substituting in. And now we can simplify. Okay? Working inside the parentheses, okay? 0 minus 1 is minus 1. That's going to be squared. 0 plus 3 is 3. And then 0 minus 5 is minus 5. And it's going to be cubed. Okay, let's start simplifying. Negative 2 times, well, negative 1 squared is a positive 1. We'll leave that 3 there. Okay. And then negative 5 cubed. Well, a negative cubed has to be negative. 5 times 5 is 25, times another 5. 5 times 5 is 25. 5 and 2 plus 2, 125. Okay. Alright, now let's combine these. Okay. 2 times 1 is 2, times 3 is 6. Make that negative. So we have negative 6, these 3. And then still times this negative 125. Okay. Now I've got to take 125 times 6. 6 times 5 is 30. Carry. 6 and 2 is 12. Plus 3 is 15. 6 times 1 is 6. Plus 1 is 7. Okay. Then a negative and a negative become positive. So when you evaluate that, you get positive 150, or 750. So that means our y-intercept is 0, 750. Okay. So those are the y-intercepts. Now, the other important graphs that we need are the x-intercepts. Okay. Now, the x-intercepts come when we let the function equal 0. So, we're going to take negative 2 times x minus 1 squared times x plus 3 times x minus 5 cubed, and let that equal 0. Now we've got this coefficient out here, negative 2. Let's just divide everything by negative 2 to get rid of it. So the negative 2's will cancel. And 0 divided by anything but 0 is 0. So now by the zero product property, it's either that x minus 1 squared equals 0, or x plus 3 equals 0, or x minus 5 cubed equals 0. We'll do the easy one first. This is x is equal to negative 3. Remember, this one means x minus 1 times x minus 1 equals 0. So if you reapply the zero product property, we have x equals 1 or x equals 1. So x equals 1 has a multiplicity of 2. Okay. This has a multiplicity of 1. And here, I hope it's clear that x equals 5 is a solution, but it has a multiplicity of 3. So we could split this up 3 different times. Alright, let's see if we can say anything about the degree. Well, first of all, let's see here. So we have a multiplicity of 2. That means, let's see, our x-intercept here is going to be 1, 0. And because this is even, this will be tangent. This means negative 3, 0 is an x-intercept. Because the multiplicity is odd, it will cross. This means 5, 0 will be an x-intercept. This multiplicity is odd, so it will also cross. Okay, now we need to talk about the degree of the polynomial. So here's a multiplicity of 2, that's 1, and that's 3. So if you add all these up, 2 plus 1 is 3, plus 3 is 6. This has to be a 6th degree. You can also read that from here, but be careful, you only can do that when these are linear. So here's 2, 3, and 3 more is 6. I know that because ignoring this negative 2, if I multiplied everything out, this would be an x cubed. Then I'd have to multiply it by this x to get to an x to the 4th. And then this would be an x squared, an x to the 4th times an x squared would be x to the 6th. And since these coefficients are 1, it would be 1x to the 6th. But our leading term here has to be multiplied by negative 2, so our leading term is negative 2x to the 6th. Okay? So this is a negative 6th degree. You would find that if you multiplied everything out, but don't waste your time doing that. Okay? Make sure you can just read these things from here. Okay, so let me just simplify everything again before we go. We have zeros at negative 3, 1, and 5. The multiplicity of negative 3 is 1, so it will cross. The multiplicity of 1 is 2, so it will be tangent. The multiplicity of 5 is 3, so it will again cross. We have a negative 6th, so that means the end behavior will have to look like this. And we have a y-intercept of 0, 750. Okay. Now, we're just going to sketch this. So let's try and put it all together. So negative 3, we'll say is here. This is negative 3, 0. Don't hash these things out. Just go ahead and label them to make it true. Okay. 5, 0. So these are our x-intercepts. And we can label this to make it true. Let's call this 0, 750. Okay, that'll be our y-intercept. And we know the end behavior looks like this and like this because it's a negative 6th degree. Right. Now, here it needs to cross. Here it needs to be tangent, and here it needs to cross. Okay. Now we're just going to connect the dots. Okay. So I'm starting down here with the ending behavior. I'm going to come up to my y-intercept, and it will cross. Now, it could be doing other things in between here. It could go way up and then come back down. We don't know. But eventually it's got to come and cross through here because it's a y-intercept. And then this next 0 is pulling the graph down towards that. Now when it gets there, because the multiplicity is 2, it's going to bounce back off. And it could go all the way up, it could just go slightly up, it doesn't matter, we don't really know, but as a sketch, it'll go up and then it has to come back down. This 0 is pulling the graph back down, and eventually it'll cross and connect with this. And so this is a good sketch of the graph with all the important information. Okay, so when it's in factored form, everything comes across very easy. We can just do a little bit of manipulations and answer it. Okay. Let's do one more where the function we're given is not in factored form. Okay. So for example, if we have f of x is equal to 10x cubed minus 100x squared minus 5x plus 10. This is an expanded form, so it's pretty easy to answer than the y-intercept question from here. If we let x equal 0, this goes to 0, this goes to 0, this goes to 0, the only thing that will remain is f of 0 has to be equal to 10, so our y-intercept is 0, 10. So that was easy to answer. Now for our x-intercept, oh, actually, what else is easy to answer? Well, we can answer the degree. Okay. We know this is a third degree, and it's a positive third. Okay, so what will that mean? That means end behavior needs to look like this. Okay, so that's good. And now we need to solve where f of x is equal to 0. That is, we need to solve 10x cubed minus 100x squared minus 5x plus 10 equals 0. Okay, so let's do this one. We can do some factoring by grouping. Here, in this one, I can pull out a 10x squared, and that will leave behind an x minus 10. Oh, I hope this works. Factoring by grouping might not work on this. If I pull out minus 5, then we're left with x minus 2 equals 0. So that's not going to work by factoring by grouping. So I think what this really was supposed to read is 50. Because then when we pull out the minus 5, we have x, 10 minus x. Okay, so let's change that up here as well. Sorry, you guys. So this would be 50, so this is 50. Okay. Alright, now we can factor out the x, 10 minus x, right? So negative 5 plus 50. Okay. So we can factor out the x minus 10s from each of them. And that will leave behind 10x squared minus 5 equals 0. Now we can split that up. It's x minus 10 equals 0, or 10x squared minus 5 equals 0. Okay. So x is equal to 10. This has a multiplicity of 1. Okay. And our x-intercept is going to be 10, 0. From here, if we add 5 to both sides, okay, and then we divide, we'll get 5 over 10. So x squared is equal to 1/2. Okay. So x will be equal to plus or minus, now be careful about this, the plus or minus, the square root of 1/2. Okay. Let's remember that we could write that as the square root of 1 over the square root of 2, which is equal to plus or minus 1 over root 2. And we could rationalize this, so x would be equal to plus or minus the square root of 2 over 2. Remember, when we're rationalizing, we multiply to get rid of the square root in the denominator. Okay. Now we have to be careful here. What we really have is two solutions. We have either that x equals the positive square root of 2 over 2, or x is equal to the negative square root of 2 over 2. So it leads to one x-intercept square root of 2 over 2 comma 0, and another negative square root of 2 over 2 comma 0. Now, even though there's an x squared here, we get two solutions, so each of these have a multiplicity of 1. Okay. So be careful with that. Just because there's an x squared in there, notice it wasn't outside, it leads to multiplicities of 1. Okay, so let's put all this together. Now these are irrational, and that's fine. We're going to just estimate where they're at. I know that this is a positive third degree, so the end behavior must look like this. I have 3 zeros. One is all the way out at 10. Call this 10 comma 0. One was that positive root 2 over 2 comma 0, and one was the negative of it. Okay. And then we also know that there's a y-intercept at 0 comma 50. Okay. Now since all of these were multiplicities of 1, they need to cross. Okay. And now it's just a matter of connecting the dots. Okay. So this one will come up, the 0 will pass through the 0, it will cross through there, come up to the y-intercept, come down to the next 0, then go down. I don't know how far down it's going to go. It could go really far. We don't have to. We're just drawing a sketch. But eventually this next 0 is going to pull it back up, and it's going to cross. And so this is a graph, a sketch of the graph, with all of the important points labeled. So this is going to take a little work. You have some homework, and then I'm also putting up a worksheet for you. But once we get the hang of this, it's going to be really fun. All right, send me an email if you have any questions.